Okay, so the things we are going to do today is to go through these 4 very important concepts. Okay, and you are going to see these questions in your homework a lot. Okay, so here you can see I written down the vapor pressure lowering, boiling point elevation, freezing point depression, osmotic pressure increasing. This is always true when you put in more solute into your solution. All right, so just memorize these 4 sentences. It can actually already help you solve many actually the conceptual questions in your homework. All right, so let's talk about the collective property. It is actually a property of solvent. For example, if today you have a solution, the vapor pressure of that solution is actually determined by your solvent, not by your solute. The boiling point, the freezing point, that property is actually mainly determined by your solvent. So think about this. If today you have water, right? The boiling point of water is very easy to understand, right? Purely determined by the water, right? If today you have sugar water, so if you measure the boiling point of that sugar water, it will still be around 100 degrees C. So let me say actually, there are certain property of your solution is mainly determined by the property of your solvent. And the good example is freezing point, boiling point, vapor pressure, and osmotic pressures. That's why we're discussing these 4 properties today. Okay, it's mainly about the property of your solvent. And then the collective property mainly describe, okay, if today you add in solute into your solution, okay, how that's going to affect these 4 properties. And then in your textbook, you're going to see, okay, collective properties are properties of solutions that depending on the number of dissolved solute, but not its type. In other words, it means is that if today you throw in 2 mole of sodium chloride versus you throw in 2 mole of glucose, it's going to have the same effect. It's actually the number of solute you throw into this solution is going to change the property of your vapor pressure, boiling point, freezing point, and osmotic pressure. Okay, it doesn't care about what other stuff you throw in. You only care about how much the species you actually throw into the water. So it's more about the numbers, but not about the species. And then the property of the solution is mainly determined by the property of your solvent. And then what we are going to understand is actually why when you throw in the solute, this 4 property is going to change. We want to understand how the solute particles is going to affect it, okay? And the main reason is because the solute molecules actually get in the way when these 4 properties actually occurs. So I guess at this moment it's not very clear. What do I mean by the solute molecule get in the way? Okay. Let's start from the easiest concept, the vapor pressure. The first important question you need to know is actually, what is vapor pressure? So how is actually vapor pressure? Where is vapor pressure originate from? The vapor pressure is actually coming from the gas molecule. It hits the glass, okay, and that gives you the vapor pressure. Okay, so it's very important and very simple concept that you should know. Once you have the gas molecule inside the space of define, okay, so the way we define the space is actually if today you put a liquid into a flask, you cork it, okay, you have a closed system, right? What's going to happen is actually the liquid molecules on the surface is going to evaporate. And those evaporate gas molecules are going to hit the walls. And those motions create the overall vapor pressure. It's actually a very simple but very important concept that you should know. Okay, every time when other people ask you what is pressure, The idea you should have is actually something such hitting some area. So if you have those concepts in mind, you pretty much can answer all the simple pressure concept questions. The system, which is actually this whole thing, is not at equilibrium. The molecules on the surface start going to evaporate. Okay, and it's going to actually hit the wall, create some vapor pressure on the top. And as time goes by, you will see the water level decrease a little bit. It means actually more actual water molecules actually in the gas phase. It's hitting the wall. And then if you wait long enough, it's going to reach so-called equilibrium. So what's going to happen at the equilibrium state is actually you have constant water goes from the liquid to the gas phase, which is a process we call evaporation, right? At the same time, those gas molecules, they are not just hitting the walls, they actually collide with each other too. Okay, when they collide with each other, they condense. So when you reach equilibrium, okay, the two processes actually happening at the same rate. So you can see here, I wrote this. Rate of evaporation is going to equal to rate of condensation. So at this moment, then you are going to reach so-called the equilibrium state. And then the pressure that you measure under this very specific condition is so-called the vapor pressure of this solution. We want to actually explain the collective property of vapor pressure. How is the solute is going to affect this property? So the key to understand this is actually you need to know when a solution starts to evaporate, this process happens at the interface between your liquid and your gas. Every time you see the bubbles, when actually happening to actually evaporate, okay, it must actually happen on the surface. The concept you need to have is actually that the evaporation occurs at the surface at any temperature. So now think about this. This is the original solution you have. At equilibrium, we know the gas molecule can actually evaporate and condensate at the same rate. Think about this. If you're throwing some solute molecules on the surface, some of the area is going to be occupied by those solute molecules. And most of the time, if your solute is actually a solid, it doesn't evaporate. In other words, what you do is actually you minimize the surface molecules that can evaporate. The end result is actually, since you actually have much less molecule can go up to the air, so the vapor pressure is going to be what? It's going to decrease. So that's why we say vapor pressure lowering, because your solute molecule get in the way in this evaporation process. Once you understand the concept, the calculation you are going to do is actually so-called the Raoult's law. Raoult's law is actually the equation you can use to estimate the vapor pressure of a solution. So this is actually specific for if your solute is in the solid form and your solvent is in the liquid form. Okay, in other words, the vapor pressure is actually ultimately determined by your solvent, because the solvent is going to determine the vapor pressure. Here, the things you want to be careful is that in this equation, okay, it says the vapor pressure of your solution is going to equal to the vapor pressure of your solvent multiply the mole fraction of your solvent. That is actually the mole fraction of your solvent, not the mole fraction of your solute. Make sure you know it's actually mole fraction of the solvent, not the solute. We are going to give you one example so that you can see the things more carefully. Find the vapor pressures above a solution of 1 mole of glucose dissolved in 9 mole of H2O at 25 degrees C. And then there's actually one more information I need to give you. Given that the vapor pressure of pure water is 23.9 torr. Every time you see these vapor pressure questions, so the keyword is this, right? Once you see this keyword vapor pressures, okay, the question that comes to your mind should be the Raoult's law, where it says the vapor pressure of your solution is going to equal the mole fractions of your solvent multiply the vapor pressure of pure solvent. If today you have only pure water, that means your mole fraction is 1, right? If it's actually pure water, then your mole fraction of your solvent is equals to 1. So you know your vapor pressure is going to equals to this value, right? And today, if you add in, they say, in this case, actually, you add in 1 mole of your solute into 9 mole of your solvent. Okay, that means actually, right now you only have 9/10 of the solvent. Okay, in terms of the mole fraction. Okay, in your solution, that means actually the vapor pressure will only come in from the 9/10 of your pure solvent. So if we put these things in writing, will be, we know your P solvent is 23.9, right? The mole fraction of your solvent is, you know, you have 9 mole of H2O that's going to contribute to your vapor pressure. And then you have 1 mole of your solute, okay, and then 9 mole of your solvent. This will actually give you the mole fraction of your solvent. So once you do that calculation, then you know this vapor pressure of this specific solution is going to equals to 0.9 times 23.9. That's going to give you a value of 21.5 torr. If you actually plot these things out, where you plot out the vapor pressure of your solution versus the mole fractions of your solvent, okay, you're going to see a picture like this, just a simple straight line. And in the x-axis, you're going to see the value change from 0 to 1. What does 1 means? Pure solvent, right? So that means actually this is your P naught solvent, right? How about here? What does that mean? Your mole fraction of solvent equals to 0. That means it's pure solute, okay? Okay, so anything in between these two ends is actually a mixture, right? So here you see this straight line, okay? What it really means physically is actually the vapor pressure, okay, is purely determined by the amount of solvent you have. And it also means, in this case, the interaction between your solvent and solute is no interaction. Because if you have interactions, then the curve will actually look differently. Okay, if you have strong interaction between your solvent and solute, what it means is actually right now, when you have your solute inside your solution, it's going to attract those solvent molecules. If they have strong interaction, that means actually they're going to pull each other. And the net result is actually they make the evaporation process more difficult. Right? Therefore, if you measure the vapor pressure of that kind of solutions, okay, you will see actually it decrease compared to the ideal Raoult's law. Okay, this is actually a more advanced concept. But I hope you can actually see these things too. Okay, so if your solute and solvent have stronger interaction, then the vapor pressure will be even lower. Okay, and the main reason is simply because your solute right now pour your solvent. I don't want you to evaporate. Okay, so stay with me. Therefore, the vapor pressure is actually going to be lower when you plot the things on this plot. Let's actually another situation. Okay, so in your textbook, let's say it's actually weak solvent-solute interaction, but that is actually not a really good or precise way to describe it. So what I really want to say is actually if your solute and the solvent, they don't like each other, they actually repulsive. They're actually repulsive, okay, from each other. Okay, so in other words, they want to kick each other out. So under this case, okay, add in this type of solute into your solution. What it's going to do is actually, okay, I don't really like you, just get out. So what's going to happen is actually it's going to promote the evaporation process now. Therefore, if you plot out that curve, you will be something like that line. So here, this Rao's law, okay, all the things we discussed so far is actually your solute is in the solid state, right? And your solvent in the liquid state. But things can get a little bit more complicated. If today you have your solutes in the liquid form and the solvent also in the liquid form. Okay, so how do you actually handle a situation like this? First of all, you need to know is actually in our previous case, the vapor pressure purely coming from your liquid solvent, right? If today you actually throw in a liquid solute into a liquid solvent, both of them is going to contribute to the vapor pressure. Instead of using the simplest Rao's law, the equation you need to use for this very specific question is that the total vapor pressure, okay, of your solution is going to come from two parts. One is actually, let's say, A is actually a solute, okay? More fraction of your solute multiply the vapor pressures coming from your solute and the contributions from your solvent as well. So A is actually represent your solute. B is represent your solvent. The idea is actually still very simple, okay? It's still the more fractions of the species of your interest multiply the vapor pressures you can actually generate. Every time we will see if you have a solute and solvent that both is in the liquid form, that means both of them is going to contribute to the vapor pressure of your solution. Then to actually use this equation to calculate the final vapor pressure. All right, so with this concept in mind, let's do some practice. First is actually find the total vapor pressure above a solution that contains 1 mole of ethanol and 1 mole of H2O. Will it give you the vapor pressure of pure ethanol is this value. The vapor pressure of pure water is that value. So every time you see these little circles on top of some symbols, it means actually a pure substance. Okay, so here means actually pure ethanol and the pure H2O. So the things you need to actually know now is actually what is the status? Okay, what is the phase of your solute and solvent? Ethanol, what is the phase of ethanol? Liquid, right? What is the phase of water? Liquid. So it's actually a liquid-liquid solution. So when you see this liquid-liquid solution and you see this keyword vapor pressure, that's the go-to equation. Okay, if today you have solid solute, liquid solvent, then the go-to equation is simply the Raoult's law. Is that clear? Cool. Okay, so let's do this calculation quickly, okay? So here we know our solute is ethanol, right? Our solvent is water. It means actually to calculate the mole fraction of your solute. So you have 1 mole of ethanol, right? So you know the mole fraction on the top is actually just 1. Bottom will be the sum of your number of mole of solute and solvent, which is actually 1 plus 1. Multiply the vapor pressure of your pure solute, in this case is actually pure ethanol, right? And the P naught ethanol is 44.6. Okay, so that will be actually your first term. Second term is number of mole of water is 1. Total number of mole is actually 1 plus 1. Then you multiply 23.9. That's actually the vapor pressure of pure H2O. If you do the calculations, you're going to get a vapor pressure of 34.2 torr. So it's less simple. The next things we want to discuss a little bit more is actually, okay, so previously we only see one single curve on this so-called the fractional vapor pressure diagram. But right now, because both of your solute and solvent, they contribute to the final vapor pressure. Okay, so now if you just apply the same concept, you're going to see two curves. And then the V total is actually the things in that connects two dots. Okay, so you can actually go back home and go through your textbook. Hopefully you can understand this diagram better. So we're not going to discuss this here because I feel it's actually not necessary. Okay, so the next thing actually we're going to go to is actually telling you how does the things we learn from the vapor pressure translate to the boiling point elevation and the freezing point depression. The first things we want to learn is that, okay, what is boiling point? Okay, so here on the hangout, I think that's actually a pretty clear definition, right? The boiling point is actually the temperature where your vapor pressure is equals to 1 atm. Okay, so that's actually the very standard definition of the boiling point. So what it says is actually in order to reach actually 1 atm, that means actually your liquid molecules in your solution going to evaporate pretty fast, right? And then in the end, you accumulate enough of gas molecule like hitting the wall that eventually produce 1 atm of pressure. So now think about this. If today you add in your solute molecules into your solution, it's going to prevent the water molecule goes into the gas phase, right? So the vapor pressure of that solution is going to become lower. But in order to compensate that so that you eventually reach 1 atm of gas molecule pressure, the things you need to do is actually what? You heat harder, right? Because once you increase the heat, then the evaporation rate is going to be accelerated. Okay, and the net result is that the boiling point of your solution is going to increase. The equation that you're going to use for this specific concept is that the delta TB, which is actually the change of your boiling point, is going to equals to KB. So KB is so-called the molar boiling point elevation constant. So it is a constant multiply the concentration of your solute. So remember, this concentration is actually the molality, which is the number of mole of your solute molecule per kilogram of your solvent. The concentration unit is very specific, okay? You need to use the correct concentration unit to calculate the correct answer. If you use mole fraction as the concentration term for this equation, you're going to get the wrong number. If you use the molarity, you're going to get the wrong number. If you use the normality, you're going to get the wrong number. If you use the mass percent, you're going to get the wrong number. The only way you can get the correct number is actually using the correct concentration terms. In this case, will be molality, okay, number of mole of solute per kilogram of solvent. So make sure you know what concentration unit to use. And then most of the time, for these constants, you can actually get it from your textbook, okay? Otherwise, the question will actually provide those constants for you. All right, so that's all you need to know. Not all you need to know. I think we'll come back to that later, okay? I want to actually bring up the same concept for the freezing point depression. For the freezing point depression, freezing point was defined as the temperature where your liquid molecules start to form the solid. In order to form the solid, okay, your molecule will be form some lattice. You're going to see a crystal forming. And those lattice is actually specific to the liquid molecule you have. So think about this. If today you have some solute molecules, okay, that actually doesn't belong to your solvent. What it does is going to prevent your solvent to form those perfect crystals. That means actually introduce many imperfect situations for your water to form the ice. And the things you do is actually you keep lowering down the temperature so that your water molecule moves slower and slower, so that they can actually enhance the chance they can form the ice in the end. So in other words, the solute molecule is going to prevent the interaction between your water molecules so that they can actually solidify. So under that situation, what we do is actually lower down the temperature further, okay, to lower down the motion of the water molecule so that they can actually form the ice. Okay, and the net result is actually if you have solute molecules get in the way, you need to go to a lower freezing point for your solution to become solid. And that's why we say the freezing point depression is going to occur when you have more solutes inside your solution. Again, to calculate the change of your freezing point of your solution, the delta TF is actually change of your freezing point. It's going to equal to KF. KF again is actually so-called the molar freezing point depression constant. And the M, again, is actually the molality of the solute inside your solution. Okay, again, you have to use the molality, not any other concentration term. With those things being said, okay, you know how to calculate the temperature change, right? But in your homework, that's another thing it's going to ask you. What is going to ask you in the homework is actually, okay, if I throw in certain amount of solute inside my solution, okay, instead of asking you what is the temperature change, it's going to ask you what is the final boiling point and the final freezing point. Okay, so TEF is actually the final boiling point, okay? TFF is actually final freezing point. So the way you calculate it is actually because you know once you throw in more solute, okay, the boiling point is going to what? Increase, right? So you know your final boiling point will be the normal boiling point plus your delta TB. where TB is actually calculated using this equation. How about your freezing point? Freezing point should be, okay, your freezing point, no more freezing point, right? We know freezing point is going to go what? Go down, right? So it's minus delta TF. Okay, so this delta TB, delta TF, okay, if you look at this K, it's all positive, okay? Concentration is always positive. That means actually your delta TB, delta TF is always positive. But you need to actually really know whether you should actually plus or minus so you can calculate the correct final freezing point and the boiling point.